Let me take a look at an object in motion. It has some motion from a pre-existing push, but there's no push now. It's just coasting along under Newton's first law. The whole idea of inertia, that objects like to keep doing what they're already doing if you leave them alone. So what would it do? Well, it would go like this. If the net force is 0, the velocity is constant. Well, the velocity being constant, I will point out, that means you have to have, there's two ingredients to velocity, right? There's speed and direction. That's what we call velocity. It's the combination of speed and direction. So you not only have to go at a constant speed, but you have to have a constant direction, which is a straight line. And that is not a circle, right? If the outside world leaves you completely alone, you cannot go in a circle. You have to keep doing what you're doing in every sense of the word. You can't be going faster or slower. You cannot be changing direction. So, what can we do to make this thing go in a circle? We're going to have to exert a force on it. So, I'm going to go ahead and suggest that the net force be to the left. Now what's that going to do? It's going to nudge this thing off of its current straight line path. It's going to pull it a little bit to the left. So it's going to look like this. The trajectory can kind of curve over. Right? It's like imagining running down a hallway. Maybe this hallway outside. You notice, by the way, that there's a design flaw in this building. All the doors open outward to the hallway. It's really hazardous. Have you noticed this? This whole building? All the classrooms, the doors open out to the hallway. So you're running down the hallway and someone opens the door and hits you. Of course, it's going to cause you to veer off course, right? So, here you are. Not going in the exact straight line you were before. Now, if at that point you're left alone again, well, of course, you're going to continue doing exactly what you're already doing at that moment forever. So at that moment, whatever speed you have and whatever direction you have is then maintained from then on. Well, then again, you will fail to go in a circle because anytime someone leaves you alone, you maintain the speed and direction you have. So you can hopefully see where I'm going with this. It's not just a one-time bump, it's a continual hug, okay? So we're going to have that the force still is there, F net, so that it's going to pull you off that straight line path. So you don't go outward forever in that straight line. You get curved off that path. So you might go like this, and now you're doing this. And again, if at any point the force releases you, you're not going to stay in a circle simply because you want to. The whole idea of inertia is that once you're left alone, you maintain the exact speed and direction that you have from then on till forever. So the net force is going to have to continue to hug you in. So I guess I'll go ahead and complete this. That's how you go in a circle. You basically need a force continuously hugging you into it so that you don't fly out in a straight line. Okay? This is a basic bit of physics that you often see gotten wrong. There's a scene at the beginning of the movie Gravity that took me right out of the movie because you had someone who was spinning because they were attached to some kind of like mechanical arm or something like that. And then when they became loose from it, they just kept going in a circle for no reason, right? As soon as you jump off the rotating body and there's nothing holding you in there anymore, you just go straight with exactly the motion you had at that moment forever, okay? things don't go in circles because they just somehow naturally want to do that. How would they even know what circle to move in? What radius would you go in, right? Newton's first law tells us that there's only one thing you can do if you are left alone, and that is exactly the same thing you were doing a moment later that you were doing a moment before. The exact same speed, and most crucially, the exact same direction, okay? If you want something to go in a circle, you're going to have to continuously work for it. Hug it in. Apply a net force toward the interior of the circle. In fact, if I have drawn this correctly, which I sort of maybe have, I intended for all of these forces, one of them, I'm going to have to cheat a little bit. These are all supposed to be pointed radially inward toward the center of the circle, okay? Question?
Yeah, so this is like the idea of centrifugal force, pretty much?
Yes, so we'll talk about centripetal force and centrifugal force in just a moment. Question?
When you're going around, when your velocity is changing so that you go in a circle, is that accelerating?
Yes, yes it is. So we're going to have to expand our idea of what acceleration means, right? Acceleration is any change to the velocity, even if it's just a directional change. So while you may be used to acceleration being speeding up and slowing down, acceleration could also change your direction of your velocity. So for instance, things in your car that accelerated, not only the gas pedal and the brake pedal, but your steering wheel. Every time you turn the steering wheel, you're accelerating your car because you're changing the direction of your velocity. Not the speed, but the direction. So let's actually summarize this. So for circular motion, you need a continuous inward force as necessary. Now, that inward force could be caused by a number of different things. You just need some force to step up, or maybe even some combination of forces that is going to step up. We give a name for the amount of force necessary. It's called centripetal force. And that's a name that's basically the bane of my existence because it makes it sound like it's another force to add to the list, like normal force or tension or frictional force. It's not. Centripetal force is a name for the required amount of force that you need. You don't get it just because you want it. Other forces are going to have to step in and provide it. Okay? So this is a requirement. So anytime you hear centripetal force, think required force. So centripetal is just a name for the amount of force that's required to be provided by somebody or something if you want to go in a circle. Going in a circle is a privilege, not a right, and something or some force or forces are going to have to step up and meet this requirement. If they don't, you fail. You won't go in a circle. Okay? Now, before I tell you a little bit more about that, I do want to get one thing out of the way. You may notice that I drew the net force purposely perpendicular to the velocity, right? And the arguments that I made for trying to get it to go in a circle were more rough and conceptual. So I made the analogy if you're running down the hallway and someone nudges you to the left, you're going to get pushed to the left, but certainly that does not require that the force is exactly 90 degrees. So let me talk about that first. Why did I draw it at 90 degrees? Well, first of all, the net force and the acceleration always point the same way. That's Newton's second law. You can always count on that. The net force and acceleration always point the same way. So I have that the velocity and acceleration are perpendicular. Why did I draw it that way? Well, I drew it that way because that is the simplest example of circular motion. So let me explain what would be so wrong or bad about having the acceleration not going exactly 90 degrees. Well, the answer is not much, but it's a little bit more complicated, and we're going to tackle it a little later in the course. So here's what I'm going to do. If I have that the acceleration and net force point at some random angle, not necessarily 90, I can split the acceleration into two components. I can split the acceleration into a component like this and a component like this. Now normally, of course, we call the components x and y, right? Here I'm going to give them slightly different names. I'm going to call them A tan, that's for tangential. What I mean by tangential is, of course, is tangential to the circle. So is the velocity, so these are going to be along the same line. And then this other component is centripetal. So one of the things that's handy about components, of course, is that you can imagine each component as kind of its own thing. So let me copy, along with the velocity, let me copy in A tan. A tan looks like this. Now this is stuff that you should know for your first exam. What happens when the acceleration and velocity are the same way? You're going to speed up. So this you're going to speed up. But you're going to live on that line, that axis forever, right? So you can speed up or slow down going along a line, but you always live on that line, right? So those are the only two options for A tan, is it either can point with the velocity and speed up the object, or against the velocity and slow it down. But you live along this line. You'll never not live along that line if A tan was all you had. In contrast, if you have this velocity, A centripetal forms a 90-degree angle with the velocity, and this is where we have to broaden our definition of what acceleration can do. If you have a component of acceleration that's perpendicular to the velocity at all times, it never has a component with the velocity to make it go faster, it never has a component against it to go slower. The only thing that this serves to do is to move the motion off the current line onto a different line. So if you have a current motion along this line, and you apply that kind of acceleration, what it'll do is it'll shift it so it's now not along this line, but another line. So what this does is it changes the direction. So that is what we are now moving into, is this idea that acceleration can actually do more than just make something go faster or slower. So what we said was that acceleration is generically what is the instructions to how to change the velocity, right? But velocity has a speed and a direction. And so what we do, just to kind of wrap our heads around this, is to think, well, if the velocity has two pieces, speed and direction, let's break the acceleration into two components, each of which controls one of those aspects. So if we break it up into A tan and A centripetal, A tan changes the speed, but doesn't change the direction. Now, I'm being a little bit flip about that because, of course, you know what happens if you apply A tan against the velocity long enough. What will happen?
Slow down.
Slow down, and then what happens? Stop, and then speed up the other way. So isn't that a change in direction? Sure. But I mean, like, it has to be along that line, right? You can't move off that line if A tan is all you have. Acentripetal, it's the other way, right? It has no effect on the speed, but it changes the direction. It moves you from this axis onto another axis. So you see we've just kind of come up with roles for this just to get our heads around it. So if acceleration is the change in velocity, that we have to broaden what that means far beyond what is usually used in everyday language. Again, as I mentioned, yes, you have in your car, you have your gas pedal, you have your brake pedal. Those are things that can change A tan, right? Those are things that can make you speed up and slow down. But if you turn your steering wheel, you are also accelerating your car because you're taking it off the line that you're driving on and moving it onto another line. An object would never spontaneously do that. It does that because of a force and acceleration that causes that. Okay? So think about that next time when you're driving a car. Every time you turn the steering wheel, you're accelerating it. It's not accelerating the way we might use in everyday language, but it fits the criteria, right? It's a change of velocity. It's just a change to the speed part of the velocity, or the direction part of velocity, rather, not the speed. So, here's what we're going to do. This is for later. We'll come back to that. I think it's homework number 8. You want to mark that down. Although if it's not important, we'll get to it later. We don't want to have to do too much at once. We don't want to have to worry about not only how do you go in a circle, but how do you go in a circle while going faster and slower. Now, of course, you know that's possible, right? It's possibly going in a circle, going faster or going slower, but one thing at a time. So for right now, we want to just focus on what it takes to go in a circle, okay? So we're going to focus in on the centripetal part, okay? So if you go over here to my original diagram, why did I draw the net force and acceleration exactly perpendicular to the velocity? It's because I didn't want to have to mess around with the speed change yet. So this is going to be going in a circle at a constant speed. So this is a constant speed circle. This is where you hopefully appreciate the difference between constant speed and constant velocity. Because it is constant speed, but it is definitely not a constant velocity. You're going in a circle, so you're constantly changing your direction. Okay? Your velocity is not constant. Your direction is every moment something new. But your speed is constant because you're applying that force and acceleration just so, keeping it at 90 degrees, the velocity, so it never has a component with or against the velocity to slow it down. It simply keeps it turning. We call this uniform circular motion. So uniform circular motion is kind of another way to say circular motion at constant speed. It's the simplest kind of circular motion. It's what we'll take a look at first. So what does it take to go in a circle before we worry about speeding up and slowing down as we do so? Okay? So in this case, in uniform circular motion, A tan is 0, A centripetal is not. And so there's really no distinction at this point between the total acceleration and A centripetal. But I do want to use the proper terminology. I'll call it centripetal because later on, of course, centripetal won't be the whole story. Are there any questions on that before I move forward? All right, so the next question, or the next thing to address, how much force do we need? So we need to address the size and direction of the centrifugal force. We already know the answer for the direction is inward toward the center of the circle. I guess I should put that toward the center of your circle. And how much force do you need? Well, the amount of force you need will, of course, be determined by the amount of acceleration you need. That's just Newton's law, right? Newton's second law. And here is where I'm going to have to pull out of thin air the amount of acceleration needed. The acceleration that you need to go in a circle is determined by how fast you want to do it and what radius of circle you want to make. So I go over here, and completing it, mv squared over r is the amount of force it'll take to go in a circle. You need that exact amount of force to go in a circle. If you don't have it, you will fail. How much force do you need? The answer is not always 5 newtons. It's determined by the mass that you want to take in a circle, how fast you want it to do that circle, and the radius of the circle you want it to make. Okay? Now, because I pulled that out of thin air, I do want to talk about why it makes sense. But first, let me just sketch what happens if you fail. So remember, this is a requirement. What happens if you don't meet the requirement? Okay, what happens if you fail? Well, there's a couple different ways to fail. What if the actual force that you pull into the center is too small? What do you think would happen if you have some object that's going along, you're trying to hold it in a circle, trying to hug it in, and that force isn't enough? Or maybe it's even not enough, like it's 0. What happens? How do you go relative to the circle? Do you stay in it? No. Where do you go? You fly out. Exactly. So here's how you fail if the actual amount of force toward the center is smaller than necessary. You fly out of that circle. Of course, the case that's easiest to see if the actual amount of force inward is nothing, 0. Then Newton's first law tells us you go out of the circle in a straight line. You don't pull hard enough, so you don't hug it in enough. You could, of course, fail the other way. What if the actual amount of force is greater than the requirement? You hug it too tight, right? You pull in harder than you should. What's going to happen to the circle now? It's going to you're actually literally going to pull the object into the center of the circle. So it's going to collapse inward. You hugged it too tight. There's lots of spectacular ways to fail going in a circle if you don't meet that very specific requirement. Going in a circle is a privilege, not a right. This is the Goldilocks situation. The Goldilocks situation is that the actual amount of force that you exert is going to be exactly what is required by this formula. Then you have this strange state we call circular motion. You have an object that has a velocity, and it is accelerating towards the center of the circle. Except now you have to really kind of wrench your mind around what it means to accelerate towards the point. Because you're accelerating towards the center of the circle, but you're never going to get any closer to it. If all goes well, you'll maintain the distance from the center of the circle. You're accelerating towards a point that you will never get any close to. Now, if you think that's weird, think about this. If you didn't do anything, you would certainly fly away, right? If you weren't accelerating toward that point, you would fly away and be gone. If you pulled hard enough, you could actually collapse it. So what we've done is we've achieved this Goldilocks situation where we're accelerating toward the point just enough So we don't go further away, but not so much that we actually go closer. We just maintain the distance from the center. Okay? Does that make sense? So I know it's strange, but you have to kind of expand your definition of what acceleration means. Here are the acceleration functions to continue to change the velocity's direction to stay on that circular path. So let's take a look at the formulas in here, or the formula here. And I'm going to try to convince you, since I just pulled it out of thin air, why it makes sense. Okay? So according to this equation, if you go faster, right, if v is increased, what does that mean to the amount of force that's required? What's that? Increases, right? In fact, that's a nice square proportionality, which means that if you go twice as fast, how much more force do you need to hold that turn? 4 times, right? So you go faster, you need to pull harder to hug that turn. Okay? Let's take a look at radius. If I decrease the radius, what happens to the force? It increases. So if I try to take a turn faster, or I try to take a sharper turn, right? A very, very quick turn is a very small radius turn, right? Both of those mean I'm going to need a lot of force for that, right? So, again, going back to driving, right? If you want to take a very, very tight turn at a very, very fast rate of speed, you need a lot of force for that. That's when you're in danger of maybe not getting it, right? If you plug into the formula and you find that you need, say, 100 newtons to hold that turn, the world is under no obligation to provide 100 newtons. And if it can actually only provide less than that, guess what's happening? You're not making that turn. You fly out. You see this all the time, right? People try to take turns too fast, too tight. They ask more of force from the world than the world is willing to provide. Remember, what we calculate from this is simply the requirement. The actual world has to step up and give it to you. If it can't, you fail. Okay? So, advice for rainy days, right? On rainy days, the ground is slippery. The amount of frictional force, which by the way usually provides your actual force that's going to hold your turns, the actual frictional force available is much smaller. So drive slower. Take more gradual turns. Right? Good advice. Why should you drive slower and take more gradual turns? It's because then you're asking the amount of force required to hold those turns is smaller. And then the real world might actually be willing to provide it, right? Does that make sense? This, by the way, also I should point out, depends on mass. So if you have more mass, you need more force. Remember what mass is. Mass is a measure of inertia, how stubborn you are to change. That includes all kinds of changes, even directional changes. If you have a gigantic truck with a lot of mass, it is much harder to change its trajectory. So you will often see that if you have very large vehicles, they don't go zooming around super fast with super tight turns either, right? So those are all things that can impact how much force you need to hold a turn. How fast you're going, how massive you are, and how tight of a turn do you want to make. Question?
Are those circles uniform circular motion? Can you include constants?
These here?
Yeah, all
This one actually makes it. Here, this fails by flying out, and this fails by collapsing inward. So these are intended to show the not enough force, too much force, and Goldilocks, just right. Okay.
So you're analyzing the formula to try to tell us like how those variable change influence those.
So what I'm telling you here, this is the amount of force that you can calculate is required. So that goes in here, right? And then the second piece is if you actually get enough force from the environment to meet that requirement. So for instance, if you computed that this came out to be 100 newtons, so you need 100 newtons to make that turn. If you actually only get, say, 50 newtons from the outside world, you're going to fail. You try to take that turn too fast, or too sharp, or something. If you had a situation where the actual amount of force was 110 newtons, well then it collapses inward. It's only if the outside world is willing to provide exactly the amount that's required, based on what you're trying to do, then you are successful. And in fact, that's a good point. I want to write it here, is that one or more real-world forces must provide the centripetal force. Remember, centripetal, think requirement. So things that we might ask to provide the centripetal force or required force, the same kind of forces we've already looked at. I already mentioned friction might help you when you're trying to take a car to turn. Maybe you have something tied to a string. Then the string can provide tension. Tension can be a centripetal force. Maybe the ground, normal force. These are all different things that could help you to meet this requirement. Okay? Are there any questions before I do a little bit of examples to kind of show you how this works? Okay, oh, and then one thing I did forget to mention, this was brought up earlier, centrifugal force. So you probably heard this term as well. What this is a perceived outward force when you're going in a circle. You feel like you're being pushed out, okay? So this is an outward force in circular motion. I'll give you an example. Here you are in your car, driving forward, put you in the driver's seat here. You decide to take a right turn, like that. It feels to you like you're getting pushed out of the turn, right? You might feel your shoulder going up against the car door, right? And I'm here to tell you that it doesn't exist, okay? If you retrain your brain, you can realize what's really going on. Here's what's happening. Your body has inertia. It doesn't want to change. So at this moment, it wants to continue doing this. It wants to go out of the circle in a straight line because that's what things do. They naturally always want to continue on whatever motion they have at the moment. What happens is you're not used to being in a state where you're continuously feeling uneasy about being made to do something else. It's actually the car door and the seatbelt that are saying, hey, we're turning. They're actually exerting an inward force on you. Now you're not used to inanimate objects exerting a force on you. But the force is inward, it's not outward. Now if you need further proof of this, let's imagine a scenario which I don't recommend that you try at home. Take off your seatbelt and open the car door, and then take a right turn. Now don't get me wrong, you're going to fly out of the car. You're going to fly out of the car because your car is going to take the turn without you. You're going to go in a straight line. But you go in a straight line precisely because of the absence of any force holding you inward. Okay? You're not being pushed out. You're actually going out of the circle because you have no force acting on you. And the car does have a force inward to hold the turn. So basically what you're feeling is that your own inertia, you want to go straight, not because of a force, but because of the natural inherent tendency that every object has to want to continue to do exactly what you're doing. It's the car door and the seatbelt that say, hey, we're doing something else, we're doing something else, we're doing something else, continuously. Because in this circle, you're completely always in an unnatural state. You're continuously being hugged into it. Okay? So there is no outward force, doesn't exist. Don't get me wrong, you would go out of the circle, but not because of a force, because the absence of a force would continue you in a straight line when the car had a force to bring it inward. If you can really get your head around that, then you will be able to visualize when you're taking a turn that it's actually an inherent unnaturalness that your body's experiencing, and that's what is making you feel like you're going outward. You're being pushed outward. You're not. You're just not normally accustomed to experiencing your own inertia on a continuous basis. The fact that you're stubborn and you want to continue to do exactly what you're already doing, and you're continuously being forced to do otherwise. Are there any questions on that? All right, so let's do some examples. I want to start pretty slow. In fact, this one is going to be more conceptual than anything. I'm going to go out into deep space. I mean very far away from anything that could be exerting a gravitational pull, so I can literally pretend that gravity is turned off. I'm going to have a spaceship with me. That's how I'm going to get to deep space. I'm going to have a bucket of some kind, like this. And I'm going to tie the bucket with a string to my spaceship, not depicted, because you don't want to see me try to draw something complicated. Okay? And I'm going to give the bucket some pre-existing motion. In fact, let's go ahead and say that the speed of the bucket in the past has been given a speed of 1 meter per second. Let me say that the length of this situation is basically going to set the radius. Let's say that's, I don't know, 2 meters. So if this bucket had its way, if there was zero net force on it, it would continue like this. But that means the string would snap, because the string connects the bucket to the spaceship, and the spaceship's not going to go along with it. And so in order to not get snapped, the bucket is going to have, the string is going to have a tension, and I want to know what the tension is in it. And I also want to know how many forces act on the bucket. Okay, so let's take a quick poll here. In terms of how many forces act on the bucket, let's talk real world forces, okay? Who would say 0 forces? 0 forces act on the bucket because it's going at constant speed. Okay, great. Definitely not 0. I guess I already gave that away because I asked for the tension, right? So a common misconception here is that if something is going at constant speed, it has 0 forces or 0 net force on it, but we know that can't be. You can't go in a circle if you have no net force. You go in a straight line. Okay, how many people say 1 force? 1 force acts on the bucket. Okay. How many people say 2 forces? Okay. So tension's 1. What's the other? Centripetal is not a force. It's a requirement that other forces have to meet. There is only 1 force that acts on the bucket that is the tension. There's there's not a tension and a centripetal force. The tension is the centripetal force. Remember, the tension is what's providing the required amount of force to go in a circle. Okay? So the tension is the force that will hold the turn. So the tension is the centripetal force. Okay? They're not two separate forces. There's no separate entity in the world whose whole job is just to make things go in circles. Okay? There's no magic L's that don't touch anything unless you want to go in a circle, then they suddenly run in and cause a force. It's the same forces like tension, normal force, gravity, friction, that sometimes make objects do something else, and sometimes they make them go in a circle. The only difference is going in a circle is such a privilege that the amount of force necessary is a very specific amount computed by that formula, mv squared over r, and we call that requirement the centripetal. Okay? So what we do is we set the actual forces that act and equal to the required force. The actual force that acts is tension. The amount of required force when you're going in a circle is mv squared over r. Now, here is where there is some kind of conceptual fallacies that get perpetuated because people, like kind of two wrongs make a right. Let me explain. The tension always pulls. So it's inward, right? The tension always pulls. We can always safely draw it pointing away from the object of interest. And some people look at that and they go, oh, well, that's being pulled downward, but it's not going downward, so something must cancel that. And they accidentally attribute, and I hesitate to write this down because this is so wrong, okay? They say that there's a force outward that cancels it. And then they say that these two cancel somehow, and they come up with this equation, which actually, two wrongs made a right because it's correct. Except for, here's the problem. If these two forces cancel, what's your net force? 0. What are you going to do then? Go in a straight line, not a circle. So there's a number of things wrong with this logic. So please don't do that. There is no outward force. There is only one inward force. That's the force that hugs the turn. It's the tension. And it is having to be equal to this. We can compute, oh, I forgot to give you the mass, I guess it's 1 kg, the bucket's 1 kilogram. So if you computed this, you would find that the amount of force required to hold this mass at this speed in this radius orbit would be, let's see, 1 times 1 squared over 2, that's going to be 0.5 newtons. So the tension, if the tension is capable of being 0.5 newtons, we get to go in a circle. Okay? Now, if the string snaps, if it can't provide 0.5 newtons, right, then you fly out. But if we assume that this tension is under the breaking strength of the rope, of course, then the tension can vary as needed, right? That's the whole deal with tension, right? It varies as needed. Here we need 0.5 newtons, and the tension is glad to be that, right? As long as that is within the realm of 0 tension and the breaking tension, as long as it's in that range. So again, not a lot of computation here, but hopefully it gets you the idea of the concepts. There's one force acting on this bucket in totality, it's the tension, and the tension, therefore, is the centripetal force. What I want to do in the next example is have that multiple forces combine to do this job. Okay, so instead of just the tension doing it alone, we're going to have multiple forces. So I'm not going to get too far on this today, but let me sketch out the next example. We'll do this exact same thing back on Earth. So if you've ever tried swinging a bucket of water like this in a vertical circle, right? It's kind of fun, right? If it's filled with water, it still won't fall out. Okay, so let's take a look at the physics of why that works. Put some water in it. So there, hopefully will indicate my vertical orientation. It's going to go like this. Then draw the bucket again down here. So there is my situation that I'm going to analyze next. And just to give you a little bit of a preview, of course, tension always pulls. So the tension is going to act like that at the top and the bottom. And then gravity is always downward, which means that gravity is inward to the center of the circle here, but it's actually outward over here. So what we see is that there are multiple radial forces, and we have to make sure how these forces combine such that we always get our requirement toward the center. So I'll take that up next time.